All right. All right, we've been away for a little bit. Just as a reminder, we're all a little bit sluggish. pH is an acidity scale. It tells us what the availability of the H plus ion is. So we take the log to the base 10 of the H plus concentration, because that value for concentration is going to be a small number. The log of small numbers are negative, so this negative term here gives us a positive value, and it runs from 0 to 14. These being acidic values and these being basic. The acidic values showing us larger H plus, and the basic values being smaller H plus. 7 being neutral. If your water is completely neutral, then the amount of H plus and OH minus, the amount of acid and base, is equal, and we're going to measure everything relative to that. There's a value called Kw, which is 1 times 10 to the negative 14. That's the ion product of H plus and OH minus in solution, each of them being 1 times 10 to the negative 7 moles per liter. Okay, so when the amount of H plus is larger than the amount of hydroxide, you are acidic. When we say smaller here, it means smaller than the value at neutrality. Okay, and then we got this new thing. And it's an oxidation scale. Where this is just the negative log to the base 10 of the available potential, the electrode potential, that says what the availability of the electrons is. And this gets to be quite useful. We did show this a full week ago, no, more than that, 2 weeks ago. We've been off for a little bit. This map of PE versus pH of what my environment gives me in terms of dissolved ions. Okay. Now, values of PE aren't quite as constrained as they are for pH. These values are allowed to go positive and to go negative. And low PE values mean that electrons are readily available, so that substances that are dissolved in water are going to get reduced. So low values of PE means you are in a reducing environment. And high values of PE means that you're in an oxidizing environment. Okay, and we have a couple of things in our own preserve that, hey, we're really interested in what the potential levels of iron 2 versus iron 3 is in this stream based on what my ion oxidizing bacteria are up to. So numbers can be negative.
exactly what my constraint is. All right, let's do an example or two from the book and see if this looks like it could be usable to us.
So question 1011 says,
find the PE value for acidic water at which the ratio of concentrations of iron 3 to iron 2 is 100 to 1.
find the PE for acidic solutions where the ratio of concentrations of iron 3 plus to the concentration of iron 2 plus is going to be 100 to 1.
Just making sure that I've read that correctly and I've not got it upside down. Okay. Am I in an oxidizing environment or a reducing environment?
Reducing? Wait. No, oxidation.
Okay, let me back up. I have iron 3 and iron 2, and they're both coexisting. One of them is dominant, but they are coexisting. Let's do it this way, because I'm going to put an equilibrium in here, okay? So it could be this way or that way. I'm going to have iron 2 here and iron 3 there. As written on the board, and it's not complete, as written on the board, is that an oxidation or a reduction?
An oxidation, right? It's going from 2 plus 2 to 3 plus 2 plus 3 plus?
In an oxidation, the oxidation state or the oxidation number increases. Now, oxidation numbers can be negative and they can be positive. So when I say increases, I mean gets more positive. Okay. So to go from left to right, to go from 2 plus to 3 plus, I have made this number become more positive. So this in this direction is an oxidation. In that direction is a reduction. Can we remember from Chemistry 1 what our textbook definition of an oxidation was?
Loss of electrons.
Oxidation is the loss of electrons. To go from 2 to 3, how many electrons have I lost? Just the one. Which side of the equation do I write it on?
The left side. Plus electron, right? Yeah. Okay. Right?
Because it's just fundamental stuff, and it's stuff that we know, and then as to
It's on the
explain
right side.
stuff that we know is, yeah.
That's
So,
on the right side.
as written, this says, take this and add an electron to it to get this. And that's not true. Oxidation is the loss of electrons. So we have to give that electron away. Oxidation is the loss of electrons. And to go from 2 plus to 1 minus means we lose 1 electron.
Okay. Now, it would be great
If we could complete the question with only the knowledge that we have. But we need more. And this is the only information that it gave in the question. That's all that the question states. It's at the top of page
427. It says find the PE value for acidic water in which the ratio of concentrations of iron 3 to iron 2 plus is 100 to 1. It gives us no other information, which is a bit of a Swiss. It doesn't tell us what the pH of the acidic solution is, and it doesn't give us any other information. However, if you read the text, and you have to read the text,
there's a little note. And it says, for this reaction, PE equals 13.2.
plus
The log of the oxidized species divided by the reduced species.
it would be nice if we had a way to access how the 13.2 for this specific reaction and the 2.87 for the carbon dioxide reaction that preceded it, and the 20.75 for the hydrolysis of water that preceded that in the textbook came about. But they're just given. Okay.
So, if we want to know, well, we're going to have to track that one down. Anyway, this is basically just a very quick exercise in, do we understand what a log does? Because the PE now becomes 13.2 plus the log. The ratio is 100 to 1. What's the log of 100? How many zeros are in the number? Yeah.
Two.
So logs are,
Yeah, log of 1 is
this is
0.
log to the base 10. There's a
Yeah.
little subscripted 10 right there, which means, how many zeros do I have? This gets to be 13.2 plus 2 equals 14.2. Okay, so we have,
Wait, what?
oh, 15.
Oh, yeah.
Give me a 15.2. Okay.
Which honestly doesn't make a lot of sense to us because it's the first time we've seen this number have a value associated to it. We don't know. We don't know, is that a big number, a small number, or whatever. But we do know that when the numbers are small, that's associated with reducing environments. And when the numbers are larger, that's associated with oxidizing environment. And this is an oxidizing environment because I've got 100 of those for every one of these. So this is an oxidizing environment. I might do a little bit of digging and see if I can pull up some of the chemistry behind PE and see how we can find that number. Because if we have to rely on it being given to us each time, that's fine. But wouldn't it be great if we could figure out how to measure it? Now we do have a PE electrode. Is it delivered? Did we get that one already?
It should, oh wait, I don't know about that actually.
Okay.
I don't know about it.
So we have a PE electrode. Didn't I see it?
It should be here, I'm pretty sure. I was supposed to pick up the test strips and I didn't. Is that the?
They're on the desk.
Okay, perfect.
Yeah, we have an electrode and you just stick it in and it measures. Oh, and you know where this number comes from?
Oh wait, oh yeah, it also says 13.6 is for neutral water at. Okay, I thought
Let's see if we can try and make sense of question 1010. Oh, 12. 12 seems. All right, let's do 12.
Is another one. It's going to require us to have information that is specific to the reaction. So we cannot just answer the question with the information that's in the question. We are going to have to delve a little bit. I haven't checked to see if there's an appendix.
I have the
Doubt
answers.
that there is. No, just an appendix of PE. No, there isn't. Didn't think there would be. Okay. Well, what is it, do you think, that is a major component of PE in natural water? The amount of dissolved oxygen. If the amount of dissolved oxygen determines the ability to do oxidation, which will change our value of PE. If the pressure of dissolved oxygen, partial pressure of dissolved oxygen, atmospheres. Find the ratio of dissolved carbon dioxide to the amount of dissolved methane at a specific pH, pH 4. Okay, that's all the words that are in this question. But that's not what we need. We need more than this. We need a balanced equation. And on page 426, all right, one of the things that we do in chemistry is that we balance our equations a particular way. Oh. Carbon dioxide and methane are in equilibrium in solution based on an equation that contains these components. Okay? I have carbon dioxide, I'm going to have acid, dissolved hydronium ions or protons, because a hydrogen ion only contains a proton. Hydrogen atom contains a proton and an electron. And then this side is a gain of electrons. One of the things that we can see that is, depending on whether we're in general chemistry, where the definition of what an oxidation is one thing, versus in, like, say, organic chemistry, where the definition of oxidation is much more literal. In the simplest sense, oxidation is gain of bonds to oxygen. Reduction is loss of bonds to oxygen and gain of bonds to hydrogen. In the general chemistry sense, oxidation is the loss of electrons. So as written, is this written as an oxidation or as a reduction?
It's written as a reduction.
Yeah. Because to go look at the carbon is going to lose bonds to oxygen and gain bonds to hydrogen. That is a reduction. Also, the electrons are written on the left-hand side. Okay. Our book has written this in a way because it's thinking about PE, potential. It's written it as a one electron event, which is why it looks so unfamiliar when you were talking before class. It's like, I really don't like the numbers in this book. I'm having a hard time putting my head around it. It's because it's taught in a different way than we do in general chemistry. Okay, so if carbon dioxide and acid, and now wherever the acid came from doesn't show up. So if this is HCl or H2SO4 or whatever, doesn't show up over here. Spectator ion going on there. But that's a positive. So whatever we have here, we also have to have the same number of them. These have to cancel each other out. Number of positives and number of negatives have to cancel each other out. Okay, let's see if we can do this the general chemistry way, and then we'll do it the way that it's written in the book. How many carbons and oxygens and hydrogens are on this side? How many carbons and oxygens and hydrogens are on that side? Okay. Atom count. How many carbons are there?
One.
How many carbons are there over here? We're off to a good start. This means that the carbon to methane ratio is 1 to 1. I doubt we'll be changing this number. Okay. How many oxygens are on the left-hand side?
2.
How many oxygens are on the right-hand side?
1.
I'm going to have to fix that.
Oh, I see how they did it.
How many hydrogens are on the left-hand side?
1.
And how many hydrogens are on this side?
The 6.
Yeah, it's 4 plus 2 equals 6. I'm going to fix that one last, because that's complicated. This one doesn't need to be fixed. This one needs to be fixed. What was the rule about making things balance? Do we divide them down or do we multiply them up? Yeah, what we teach is you always multiply up. So I have 2 here but 1 there, which means I need to multiply this side by 2. So that oxygen needs to get multiplied by 2 to equal 2. I find the oxygen. The oxygen is only in one place. To make that oxygen be 2, I have to put a 2 here. I can't do H2O2 and make it be peroxide, because that's not the identity of the chemical. I would be changing the chemical identity. All right, so now I have 1 carbon, 2 oxygens, and 8 hydrogens. These 4 hydrogens and 2 times 2, so it's 4, and 2 times 2 is now 8. I have 1, 2, and 8. I have 1, 2, and 1.
Oh, so then we can have 8 electrons?
Yes. So this reaction, 1 carbon dioxide is going to react with 8 equivalents of acid. Acids are H pluses, which means and be reduced by 8 electrons to make 1 methane and 2 waters. This is what we would consider to be a balanced equation. Now, why it looks so unfamiliar in the book is, let's write that again, but write it per electron. The PE is the effect of the electron, or at least its availability. Okay? There are 8 of them. So to make this be 1 electron, I have to divide that by 8, which means I need to divide this by 8, which means I need to divide that by 8, which means I need to divide this by 8, means I need to divide everything by 8. So when we look in the textbook, it says 1/8 of a carbon dioxide and an H plus and an electron combine to make 1/8 of a methane and 2/8 of a water. That is the way it's written. Yep.
That's why it looks so unfamiliar.
In Chemistry 1, if you write this down as an answer on a quiz or a test, I scratch my head and say, well, you were technically correct, but why have you just made it be so indecipherable? Okay, the reason that it's written this way in our book is that it's just this one electron at a time. I can see the effect that this guy is having.
Okay. Now, the PE for this particular reaction, written in the text on page 426. Tells us
that for this particular reaction, PE is 2.87 minus the pH plus, that's a plus, 1/8 of the log of the pressure of CO2 divided by the pressure of CH4.
okay. We can get
Half of the way to the answer. On page 4. At pH 4, PE is 2.87 minus 4 plus 1/8 of the log of that concentration. We might have to do something clever here in a second. I think we're going to have to do something clever. All right. Let me see which way the book has done this. Okay. We want to know this. So this is the term. Currently it's got a log function in front of it, but that's okay. This is the term that we want to isolate. So I want the log of the carbon dioxide divided by the methane pressures over on one side of the equal sign on its own. Okay. To get there, I'm going to move everything over. So what's going to be on, I'm going to flip this. Actually, if I flip it the other way, you'll see what happens. So PE minus 2.87 plus 4.0 equals 1/8 of the log of PCO2 PCH4. So then the log of PCO2 over PCH4 is 8 times this, because now moving this 8 across, because it's a denominator here, it will become a numerator on this side. PE. All right, 2.874 minus 2.87 equals plus 1.13, right?
1.13, yeah.
Okay. Still don't have everything that we need. There's a surprise.
Also from a little earlier in the text, it says
that for the reaction where we would have 4 oxygens and one oxygen, I'll write it the way that it's written. It's not written in the book. 1 oxygen, 4 protons, and 4 electrons. Go ahead and make 2 waters. That PE would be written 1/4 of this plus 1 of those plus 1 electron. Got to get it down to a 1 electron event. 2 divided by 4 is 1/2. The PE here is 20.75. Plus the log of the H plus concentration multiplied by the oxygen pressure. But because we only have 1/4 of an oxygen, it's raised to the power of 1/4. Okay? What I'm going to do is I'm going to substitute this value of PE into here. Because the book says that the PE comes from the oxygen. And if that's the case, then I can substitute this one in. Right? I knew that this was going to be complicated, but I didn't. It's only a couple of lines in the book, and I didn't recognize it was gonna be this big. Okay, let's see if our math skills can keep track of everything. All right, so from this line right here, PE is 20.75 minus pH and 1/4 of the log of the PO2. Oh, that's a fancy way of separating these two things. It would be nicer if we could just write that in one way this way. This is nicer. That's more complicated. These two mean the same thing, okay? Which is 20.75 minus, what's the pH? 4 in the question. And then 1/4 of the log of 0.1. The partial pressure of the oxygen in the question is 0.1 atmosphere. What's the log of 0.1?
-1. Wait,
How many zeros are there?
it's minus.
Yeah. So the log of 1 is 0. The log of 10 is 1. The log of 1/10 is -1. So this is 20.75 minus 4 plus 0.25 times -1, which is minus 0.25. PE turns out to be 16.5. Okay. All right, let's go substitute that back in where it belongs. I think we should have done that one first. I think logically, if I was writing the answer out, I would have done that. I think I might have done that part first. And then, because this, oh, we got to a place and then we stall and we wait for the other number to show up. Don't like that. I think we should have probably done that first. Okay, here we go. This is what we're trying to find. The ratio of carbon dioxide to methane is 8 times PE 16.5 time plus 1.13. So the log of PCO2 to PCH4 is 16.5 plus 1.13 equals what?
You got 149,904.
Okay. 141. All right. Our answer is in front of us. All I have to do is get rid of the log PCO2 divided by PCH4 is now 10 to the 141. Which is a very large number.
Oh, wait.
Is that right?
Well, would it be negative lot to, no, that is weird. So it's just 10 to the 141 then? My calculator won't do it.
Yeah, it's going to be an astronomically large number.
So the place where this was a negative and then turned to a positive is when I moved the numbers across the equal sign. When you move them over, you can turn. No. Yeah.
Is that, this is 12.
Huge, huge value. Okay. Let's see if this makes sense. So the answer tells us that the amount of carbon dioxide to methane in acidic water is like infinity to 1. This is a huge number. 10 to the 141 is massively in favor of carbon dioxide. Does that make sense?
Yes.
We should do it again. I know we're not going to because it took far too long, but we should do it again. What are our conditions?
It's acidic.
It's acidic. Okay, that does make a difference. The amount of available electrons does change when you move from being acidic to being basic. This is a known thing. But the thing that's controlling the PE is the amount of dissolved oxygen, and oxygen is dissolved actually quite a bit. 1/10 of an atmosphere. That means that for every atmosphere of oxygen that is above the water surface, 1/10 of it has been absorbed into the water. This is an oxidizing environment. What was the value of PE?
16.5. Is that what?
20.75. Oh no, yeah, after we 16.5. This is an oxidizing environment. The source of carbon dioxide or methane in this question, in the oxidizing environment would be carbon dioxide. In the reducing environment would be methane. In order to get to methane in water, we have to go deep down and then be in a reducing environment. Close to the surface where there's available oxygen, it's not going to happen. It's just not going to happen. One of the things that we said very, very early on, I think in the first week, when we were talking about life and death, and we're using fossil fuels, but that's okay because fossil fuels came from decaying matter, and that while we're burning fossil fuels, we have to be making new ones, yes? No,
Because the modern Earth's atmosphere contains oxygen. And that oxygen is dissolved in the water near the surface, and then it peters out as you go further down. But all of that water is in an oxidizing environment. If you want to make methane in an anaerobic environment, a reducing environment, you have to go underground, deep underwater, into a reducing environment. So this was a complicated way of telling us this does not happen. This was a quite long-winded and complicated way of the book saying you are completely outnumbered. The amount of carbon dioxide that's in the water versus the amount of methane that's going to be in the water is astronomical. 10 to the 141 to 1. Okay? All right. The remainder of this chapter is material that we've kind of seen before. It's carbonate and bicarbonate, or carbonate and hydrogen carbonate, being those two equilibria. And there's a couple of nice new ways of describing it. And then the chapter that follows is man-made interference. So the 10 is natural water, and then 11 is the human influence on water. And both good and bad. How do I take dirty water and make it clean for human consumption? And how have we taken water and made it dirty because we are not good stewards of the environment? We'll try and pick it up there when we come back. I should have practiced that question.